Hey everybody, this is a problem. It says two problems, but it's really one multi-part problem about calculating the drift speed of electrons in a wire. So let's get right to it. Calculate the average drift speed of electrons traveling through a copper wire with a cross-sectional area of 45 millimeters squared when carrying a current of 78 amps. Assume 1 electron per atom of copper contributes to the current. The atomic mass of copper is 63.5 grams per mole, and its density is 8.93 grams per cubic centimeter. Avogadro's number is 6.022 times 10 to the 23, and the fundamental charge is 1.602 times 10, that should be times 10 to the minus 19. So there's a lot of information here, and I'm just going to highlight the constants. We have 45 millimeters, 78 amps, 63.5 grams per mole, 8.39, 8.93 here and here. So we've got a lot of things going on. We're trying to find the average drift speed of the electrons traveling through a copper wire. Okay, so we know we're going to have to use our drift speed equation, and our drift speed equation was, write it out. Was it I equals N A V Q? And since we're solving for the drift speed, we're solving for V here. If I divide both sides by N A Q, N A Q, everything cancels, and I'm left with speed is equal to I over NAQ. So to get our drift speed, we need to know all of these variables. Let's check to see what we have. I is the current. We do have that. That's right here. So I is 78 amps. N is the density of free charges. I don't think we have that yet, so we don't know N. A is the cross-sectional area of the wire, and that is 45 millimeters squared. And Q is the charge on a charge carrier. The charge carrier is just an electron, so charge is just going to be E, which is 1.602 times 10 to the minus 19 coulombs. So it looks like we have everything except for little n. Density of electrons. So let's think about how we can find that. Let's look at the other things that were given other than I and A, and this is going to be Q. So we are given the atomic mass of copper. So we are given that copper has 63.5 grams per mole. We also know that the density, I'm just going to write it out. The density is 8.93 grams per cubic centimeter. And we're given Avogadro's number, which I'm going to label as capital N, 6.022 times 10 to the 23. And it also tells us that we get 1 electron per atom of copper. So really we just need to find the number density of copper atoms. That's going to be the atoms per meter cubed, or per centimeter cubed, or some sort of atoms per unit volume. Because for each copper atom we get an electron, so that's going to be the same as our number density of electrons. So N is going to be equal to that. So let's look at what we have and see if we can convert from, well, it looks like we have grams per mole. We want to go from grams per mole to, well, we want to go to atoms per centimeter cubed. Let's just think about how we can do that. Well, grams per mole, well, we know that a mole is a certain number of atoms given by Avogadro's number. So we can actually convert that to grams per atom. Let's do that. 63.5 grams per mole, and we know that 1 mole is 6.022 times 10 to the 23 atoms. So moles cancel, and we're left with 63.5 divided by 6.022 times 10 to the 23. 1.054 times 10 to the minus 22 grams per atom. Okay, so we got from grams per mole to grams per atom. Let's see, what else can we do? Notice that our final answer has atoms and centimeters cubed. Here we have atoms and grams. But our density here is a conversion between grams and centimeters cubed. That's what a density is. So we can actually convert this grams per atom into centimeters cubed per atom, or atoms per centimeter cubed. But if we want our, let's just write it out, grams per atom. If we want to end up with centimeters cubed per atom, we need centimeters cubed divided by grams. Our density is grams per centimeters cubed. So when we actually convert, we're going to have to multiply by the reciprocal of the density. We can think of this as 8.93 over 1. So when we convert this number, 1.054 times 10 to the minus 22 grams per atom, we could write that, our conversion factor as, well, we need centimeters cubed up top, grams down below, so it's going to be 8.93 and 1. Now grams cancel, and we're left with 1.181. Our units are centimeters cubed. Whoops, I forgot the power of 10. That's very important. Times 10 to the minus 23 centimeters cubed per atom. Atoms don't take up much space. So we want atoms per centimeters cubed. Well, we have centimeters cubed per atom. All we do is take the reciprocal. So our number density is just going to be, let's actually write out our process, centimeters cubed per atom to atoms per centimeters cubed. Our number density is just the reciprocal of this. It's going to be 1 over, actually let's write it as 1.81 times 10 to the minus 20, 1.181 times 10 to the minus 23 centimeters cubed per atom. Since we're doing a lot of conversions, I'm going to do divided by 1. The reciprocal is the same as raising to the negative 1 power, so let's just raise to the negative 1 power. 8.469 times 10 to the 22. And our units are going to be atoms per centimeters cubed. Okay, there's our value of n. So now we have everything we need to actually solve for our drift velocity. I'm going to fill it in here, but I'm going to fill it in red. 8.469 times 10 to the 22. And it's atoms per centimeters cubed or electrons per centimeter cubed. We can just also write it as centimeters to the minus 3 if we want, because we're just counting the number of atoms, and counting numbers don't usually have units. But there is one problem here. Our units are not going to cancel. So we are going to want to convert n and a into meters. So let's do that. So let's do that right here. convert. So n is 8.469 times 10 to the 22. It's going to be atoms per centimeters cubed. To convert my centimeters cubed to meters cubed, I know that there's 100 centimeters in 1 meter. And to cancel out all three of them, I need to cube it. Cube that whole conversion factor to cancel out the cubic centimeters with cubic centimeters, and we'll be left with per cubic meter. So it's going to be our answer times 100 cubed, getting 8.469 times 10 to the 28 per meter cubed is equal to n. Let's do the same thing with our area. Our area is 45 millimeters squared. We know that we need to cancel millimeters, there are 1,000 millimeters in 1 meter. Millimeters cancel only if we square that whole thing. So it's 45 divided by 1,000 squared. I'm getting 4.5 times 10 to the minus 5. And it's going to be meters squared. Okay, that's great. Now we have everything in base SI units, I think. Let's just check. Coulombs are good. Amps are good. Meters squared and per meter cubed. Yes, that's good. We'll get our answer in meters per second. So let's actually plug into our equation. V equals I over NAQ. It's this equation right here. Our current I is 78 amps. 78 amps over N. N is 8.469 times 10 to the 28 per meter cubed. A is 4.5 times 10 to the minus 5 meters squared. And Q is charge on an electron, 1.602 times 10 to the minus 19 coulombs. Meters cancels with meters, amps and coulombs cancel to leave us with seconds, so we'll be left with units of meters per second. Plug it in. I'm getting 1.278 times 10 to the minus 4 meters per second. Pretty slow, less than 1 centimeter per second. Okay, so that may seem like a lot, but it's mostly just converting. The hard part was actually over here, and then we just had to do a lot of conversions. In number 2, it says, in the above problem, find the time it takes for electrons to travel from the wall to the bulb of the lamp, assuming the length of the wire is 135.6 centimeters. Well, we know the drift speed V, and we know that speed is going to be, or average speed, drift speed, is going to be distance over time. So if we solve that, we get time is equal to distance over speed. So we plug in our distance, 135.6 centimeters, or 1.356 meters. Our speed is 1.278 times 10 to the minus 4 meters per second. We divide them. I'm getting 1.061 times 10 to the 4 seconds. So that's a lot of seconds. We might want to express that in minutes. To express it in minutes, we multiply by, well, there's 60 seconds in 1 minute. Seconds cancel, so we divide by 60. Be 176.9 minutes. If we wanted to convert it to hours, we would just, again, there are 60 minutes in an hour. We divide by 60 again. We get 2.9 for 8 hours. So there's a whole problem on drift speed. That's about as hard as it'll probably get. I mean, the other scenario you might have to do is you might be given the diameter of a wire instead of the area. You can do capital D for diameter. And if that's the case, you just find the area. Area is pi r squared. And r is just equal to diameter over 2. That D is diameter, not density. And just make sure your units cancel. One other thing to note, 3 hours to travel from the wall to your lamp. That's a relatively accurate estimate for how long it takes electrons to actually flow through a wire. They move through a wire. They move very, very, very slowly on average. Even though your lamp turns on instantly, the electrons themselves are moving very slowly. The only reason it turns on instantly is because all of the electrons in the circuit move together. When you push one electron, it pushes on the next, which pushes on the next, and the next, and the next. And they all travel together pretty much instantly at almost the speed of light. Hope that was helpful. Bye.